So the domain of a function is the set of all possible inputs for a function as defined by the function. The creator of the function may further restrict the domain by stating any restrictions in the setup of the problem. Now, what does that mean? When we consider all possible inputs for a function, we're really asking, is there anything we shouldn't be plugging into this function? Now, different functions have different rules. If you think about things like square roots, we don't want to take the square root of a negative number. That leads to things that we are not ready to deal with in this course and doesn't result in a number for us. So when we talk about things like the domain, we're talking about what we can and cannot plug in to different functions. Similarly, the range of a function is the set of all possible outputs for a function while considering the domain of the function. So the range tells you all possible outputs for the function. Sometimes that's everything. Sometimes you can get every single number out with no problem, but other times you can only get certain sets of numbers. Consider the function x squared. If you think about x squared, all of the outputs are going to have to be positive. So what we're going to have to do is we're going to have to go on a case-by-case basis to determine the domain and range of different functions. So let's go ahead and look at some of our examples here and determine the domain and range for each of these different types of functions. So remember our formula from before, x squared minus 2x minus 3. The first thing we want to do is we want to think about the domain. We want to consider if there's anything that we should not be plugging into this function. Again, this type of function is called a polynomial. And polynomials are pretty nice because they're well behaved and they often are easy to work with. So one of the things that I like to do when I'm considering domain and range and to think about whether or not there are things I can and cannot plug in is I ask myself, can I plug in something positive? Can I plug in something negative? Can I plug in 0? I always figure that's a good starting point. So here, if I plug in something positive, I could plug in a 1. So if I plugged in a 1 here, I would have 1 squared minus 2 times 1 minus 3. So when I carefully plug that into my calculator or calculate it out in my head, I'm going to get negative 4. I have no problems plugging in a 1. I'm also going to plug in 0. So I have 0 squared minus 2 times 0 minus 3. So here I get 0 minus 3 is going to give me negative 3. And I'm also going to plug in a negative number for good measure. So negative 1 squared is going to be positive 1. I got to be a little careful here with all my negatives. The second term, I have minus 2 times negative 1. So that actually becomes a plus. So here, this is going to be positive 1 plus 2 minus 3. And that's going to give me 0. So again, I have no problem plugging any of these numbers in. However, I really want to make sure I understand what I can and can't plug in. And sometimes it's helpful when you have a formula to draw a picture of what is happening. So here, if I were to take this function and I were to graph it, I would have a good sense of what I can and cannot plug in. So here, if I were to graph this picture, it's going to be a parabola, which looks like a cup. And it's going to come down like this. It's going to come down through negative 1, right? Because I said negative 1 has a value of 0. And then it's going to come down and turn around right about here. So I know at 1 I should have a value of negative 4. And then if I test some other numbers or if I graph it on a calculator, I will see that it's going to turn around and come back up, and it's going to come up through 3. So it roughly looks like this. It doesn't shoot off to infinity. It doesn't have any holes or weird things. I also want to look at my function and see if there's anything that contains a denominator, which it doesn't, or a square root, which it doesn't. So I'm pretty confident that my domain here is going to be all real numbers. So what that means, real numbers, is every possible number you can think of and write down. Numbers that are not real are complex numbers, things like I, which we don't consider in this course. So all real numbers. So I know what I want to say here in terms of the domain, that I can plug in anything I want. However, I don't have the mathematical notation yet to do that. So that's something that we need to talk about. So how do we write down and express this set of numbers that we've determined to be the domain of the function? So we have what's called interval notation. So there's two types of interval notation, and it's called closed interval notation. And then we also have open interval notation, which we'll talk about in a minute. So closed interval notation is used when you're going to include the endpoints of your function. Open interval notation is used when you do not include the endpoints of your function. So we need to consider if our function has any endpoints. So our function, we said we could plug in anything we want. And that goes on forever. So we could plug in a 1, a 2, a 3, a 4, a 5, and it goes on and on and on and on. So that means that I can go off to infinity in the positive direction or negative infinity in the negative direction in terms of what I can plug in for x. So that means that my interval is going to be negative infinity to positive infinity. When we talk about infinity, we always use open interval notation for that. So when we talk about this particular function, we are going to say x is an element of negative infinity to infinity. So when we talk about open interval notation, that word open means we're going to use parentheses to represent what's happening at the endpoints. The parentheses indicate that you are not including the endpoints. Now, let's talk about the range of this function. So the range of this function is interesting because if you notice, the endpoints here, they're going to go on and on forever in the upward direction, which means that the y values can get infinitely big, right? We can have 1 million, 10 million, 20 million, on and on. However, in the other direction, we do have a minimum point here, which means that the y values can't go any lower than the lowest point on this function. So how do we determine what that lowest point is? Well, like I said before, sometimes it's a really good idea to graph your function. Because when you graph your function, you can visually see what is represented and figure out where things happen. So here, I have a pretty good sense that the lowest value that I'm going to get in terms of my outputs is going to be -4. If you graph it carefully and you plug in a lot of numbers near x equals 1, you will find that -4 is indeed the lowest value, which means that my range, or my y values, are going to go from -4 to positive infinity. What you see on the left-hand side is a closed bracket. So that square bracket tells me that I'm going to include the -4 as a possible value of my outputs, and then that can go all the way up to infinity. So those are the set of outputs that I can have. So that's a demonstration of some closed interval notation and some open interval notation for continuous functions. This function is continuous because it can take on every value. So when we use this type of notation, it says that you can get every value between the two values listed. So for example, in the range, I can get anything between -4 and infinity. I could get 0, I could get 1, I could get pi, I could get lots of decimal numbers as long as they're between -4 and infinity. So this notation is used for continuous functions. So let's write this out generally. So closed interval notation for continuous functions can be written two ways. We write the independent variable, and then we write this funny looking e, which means is an element of. And then for closed interval notation, we're going to use brackets. So we're going to say a, comma b. So that means that x can take on any value between a and b, including a and b. The endpoints are included because this is a closed interval that uses these square brackets. Another way that we can write the same thing is with this notation, with less than or equal to signs. These mean the same thing. So this notation says that x has to be between a and b and can take on any value between a and b, including a or b. So it's that less than or equal to that tells us that we can include the endpoints, which is the same as using those square brackets. For interval notation, here we'll do this one with t. So let's assume our independent variable is t. We would say t is an element of little a, comma little b. So here, the open interval notation is what's important here. It's these parentheses. The parentheses tell us that we're looking between a and b, but we cannot include the a and b. So we will strictly be between them. So if a is 1 and b is 2, then t can take on values like 1.1, 1.2, but it cannot take on the value of 1 or 2, just things between them. We could similarly write this using the notation of strictly greater than or less than. So t has to be between a and b, and as long as you don't include the and equal to part of the inequality, these mean the same thing. So that's open interval notation for a continuous function. So when we're ever considering how we're going to write our intervals, we need to consider whether or not we're including the endpoints. And again, when you talk about infinity, we always use open interval notation. So let's try a couple more and see if we can figure out these intervals for the domain and range using our new notation. So next, we're going to consider a graph. So assuming that the entire function is pictured below, find the domain and range for this function. So if the entire function is pictured below, that means that it does not continue past what we see. And therefore, we can cut off our graph in terms of the independent variable because we don't have these arrows on the ends. So let's start with the domain. So the domain is all the possible x values. So here, my x values, they start at -2, and then they continue going. My function continues going all the way until I get to the other endpoint, which is at x equals 2. So my domain here, I'm going to write as x is an element of -2 to 2. And I'm including the endpoints because they are defined here and they have a defined y value. Again, I could use the alternate notation, and I could say x is greater than or equal to -2 and less than or equal to 2. Both of these are good ways to represent the domain. Now that I have my domain, I want to consider the range. So the range is the possible y values that I'm going to get from this function. And so here, if I look at my y values, I can see they go as high as 4, including 4, and as low as -4, including -4. So therefore, my range is going to go from -4 to 4 because I can get all the values in between, which we can see here. And again, if you prefer, you can use inequalities here. And since I'm including the endpoints, I will use less than or equal to and greater than or equal to symbols to represent that. So again, we can get domain and range of a function on the graph, and so far also on a formula. Now let's consider what happens when we have a table. I hope you already have a sense that we're going to have to do something a little bit different because tables are not continuous. So assuming that the entire function is represented below, find the domain and range for this function. So the domain here is going to be the values that t can take on, because in this particular example, t is our independent variable. So here, t can take on the values of 0, 1, 2, and 3. So my domain here is those values, 0, 1, 2, and 3. And then my range is going to be the values that f of t can take on. And that's -1, 1, 7, and 17. So what I need to do is think about how I'm going to represent this. So we have a little bit different notation when we talk about discrete functions. So for discrete functions, we're going to use curly brackets and we're going to list the values that these things can take on. So for example, here, t is going to be an element of, and now I'm going to list all the values that t can take on. So 0, 1, 2, and 3. So I'm listing the set of numbers that are available for t to take on to represent my domain. Similarly, I can do the same thing for my range. My range is going to be f of t, and I'm going to list all the values that f of t can take on. So -1, 1, 7, and 17. So these are the values for my range. So interval notation for discrete functions are going to list sets of numbers. So usually when we do this in general, we say x is an element of, and then we say something like n sub 1, n sub 2, n sub 3 to represent the different numbers that x can take on. Same thing when we talk about the range. So again, we're going to list the numbers that y can take on as values, or the dependent variable can take on as values in the curly brackets and as an ordered list. We write these in order generally from the smallest value it can take on to the biggest value it can take on. So that's the notation that we're going to be using for discrete functions in this course. So finally, let's go to our word problem, our description, and see what we can say about the domain and range here. So the cost of ice cream, C, in dollars at the local shop in Mathtown, Ohio, is a function of the number of toppings T ordered to be put on the ice cream. So that's what we had before. But now we have some additional information. If the shop offers 10 different toppings and the cost of an ice cream is given by 5 plus 0.25t, what is the domain and range of this function? So now we have more information than we had before. So now we've given more shape and information to this problem, and we can now start talking about different things. So the domain here are the different values that we can pick for the independent variable. Remember, your independent variable here is t. So when we talk about the domain, we're going to list it as t is an element of. Now we have to consider the different values that t can take on. Now here, the shop offers 10 different toppings. So that means we could take 1 topping, 2 toppings, 3 toppings, 4 toppings, all the way up to 10. And we also, if we wanted to, could get 0 toppings if we weren't that interested in what they were offering. So our values here are going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the values that t can take on. So that's going to be our domain, and that's how we can write it. Our range is going to be the possible costs that we could encounter at this ice cream shop. So that means for each possible value of t, there's a corresponding value of c. So in order to figure out what that value is going to be, we would need to plug each of these independent values in to get the dependent value. So for example, if we plugged in t equals 0, our very first possible number for our domain, we get c equals 5. Remember, c is cost, so that 5 represents dollars. So $5 is one possible output. If we plugged in a 1, we get $5.25. If we plugged in a 2, we get $5.50. If we plug in a 3, we get $5.75. If we plug in a 4, we get $6. If we plug in a 5, we get $6.25. If we plug in a 6, we get $6.50. If we plug in a 7, we get $6.75. If we plug in an 8, we get $7. If we plug in a 9, we get $7.25. And finally, if we plug in a 10, we get $7.50. So this is the whole set of possible costs or possible outcomes, which is the range of this function. There was a lot of data to write here, but since it's a contained set, we were able to write them all out. So that's how we would represent the domain and range of a word problem. We'd consider what the function was and think of all reasonable domain numbers, and from there generate the range numbers. So the next thing we need to talk about is something called a mathematical model, something we've already started doing, but we haven't explicitly talked about what it is. So a mathematical model is a description of a system or phenomena using mathematical functions, graphs, equations, tables, and descriptions, to represent a real-world situation. So that's something we were doing with our ice cream shop. We were representing something that could happen in the real world mathematically. Some of the functions we look at, we just look at the functions in isolation. We don't have a situation attached. But a lot of times we do have a situation, and that's why we want to get good at this modeling, so we can figure out a way to generate functions that model what's happening in the real world. So let's consider the following. A popcorn vendor at Fenway sells popcorn for $6 a bag. Let R be the revenue in dollars for one night sales, and P represent the number of bags of popcorn sold. The vendor's revenue can be modeled by R equals 6 times P. So here we have a situation where a vendor at Fenway is walking around and selling popcorn. The amount of money that that vendor takes in every single night depends on the number of bags of popcorn that is sold. And since it's sold for $6 per bag, that's where we get that 6 times P. So $6 for each bag. So if we sell one bag, the revenue would be $6. If we sold 2 bags, the revenue would be $12. So revenue is the amount of money that you take in from selling something. So here, if we wanted to talk about the independent and dependent variable, we would need to figure out which variable we would be plugging numbers into, which one varies over time. And so here, my independent variable is going to be P, which represents the number of bags of popcorn sold. So here, it can vary from 0 bags up to who knows how many bags. But that's the number, and that's the variable where we're going to be plugging in our inputs. So here, my independent variable, which I'll write as IV, is P. And my dependent variable is going to be revenue, or R, because my revenue depends on the number of bags that I sell, P. For part 2, we want to consider if this function is continuous or discrete. So here, if we want to know if something is continuous or discrete, we really need to consider what's going on with our independent variable and what types of numbers we can plug into it. So here, popcorn, it makes sense that the types of numbers that we are going to be plugging in are going to be integer numbers, things like 1, 2, 3, 4. It doesn't make sense to plug in something like 1.5. The vendor cannot sell 1.5 bags of popcorn because popcorn bags are individual units. So in this case, this function is going to be discrete because the types of numbers that we can plug in are set numbers and we can't plug in numbers between them. For part 3, we want to find a way to identify the domain and range for this function. So again, let's start with the domain. So for the domain, we're talking about values that we can plug in for P. Since it's a discrete function, we're going to use the squiggly brackets and we're going to list them. So the number of popcorn bags could be 0, right? If it's a bad night, maybe it's raining and no one wants popcorn. It could be 1, 2, 3, 4. Now we run into a little bit of problem because I don't want to keep writing numbers on and on and on for hours and hours because that would be really terrible for both of us. So in math, we have this convention where if we want something to continue, we can do ... Okay? And so here, if I write ... and I don't write an endpoint, that means technically it could go on to infinity. Now, we probably both agree that we're not going to sell infinitely many bags of popcorn, But we don't know what the upper limit is. There's not enough information in this problem to tell us what the restriction is on the upper bound of popcorn. So for now, I'm going to leave my domain as ... to say that those numbers will continue as integers as they go along. The range for the function, revenue, again, is going to be generated by considering what R values we can get from plugging the P values in. If we plug in 0, if we've sold 0 bags of popcorn, the revenue will be $0 because 6 times 0 is 0. If we plug in 1, I get 6 times 1, which is 6. If I plug in 2, I get 6 times 2, which is 12. So I can see here that I have multiples of 6 in order. And again, I'm going to use ... to indicate that that's going to continue going on. And again, I was taking those P values and I was plugging them into the function R equals 6P because that was the function that modeled our situation here. So we can take these real world problems and still talk about the types of things we were talking about before in terms of functions.